Welcome to Slumbertainment. Get comfortable, close your eyes, and let yourself relax. Tonight we explore the history of timekeeping. Please like and subscribe for more restful content. Now, let's begin. Long before anyone thought to count the hours, before minutes and seconds had names, before alarms chimed in the morning darkness, human beings lived within the rhythm of light and shadow. The sun rose, travelled across the sky, and set again. The moon waxed and waned. Seasons turned in their endless cycle. Time was not something to be captured or measured, but something to be felt, observed, and followed like a river's current. Yet even in those earliest days, our ancestors noticed patterns. They saw that shadows changed throughout the day, growing shorter as the sun climbed higher, then lengthening again as evening approached. They observed that certain stars appeared in the night sky only during specific seasons, that the moon's face changed in predictable ways, that the sun's path across the heavens shifted gradually throughout the year. These observations were not merely curiosity, they were survival. Understanding when to plant seeds, when to expect the rains, when animals would migrate, when winter's harshness would arrive meant the difference between abundance and famine, between life and death. The earliest humans did not need clocks to tell them when to wake or sleep, for their bodies followed the sun naturally, but they did need to anticipate the future, to plan and prepare. This fundamental need gave birth to humanity's first timekeeping devices, tools so simple and elegant that their brilliance is easy to overlook. A stick pressed into the ground, a stone placed carefully to mark where the sun's first rays touched the earth on the longest day of summer, a circle of standing stones arranged to capture the exact moment when day and night held equal measure. These were not merely markers, but calendars, calculators, and cosmic clocks all in one. The shadow cast by a vertical object, what we might call a gnomon, was perhaps the first clock face humanity ever knew. Someone, somewhere, tens of thousands of years ago, noticed that the shadow of a tree or rock moved in a consistent arc throughout the day. Perhaps they marked the ground where the shadow fell at different times. Perhaps they realized that when the shadow pointed in a certain direction, it was time to gather food, or return to shelter, or begin a ceremony. This simple observation transformed humanity's relationship with time. No longer were we merely passengers being carried along by the day's progression. We became observers, recorders, and eventually masters of the moments that shaped our lives. In ancient Egypt, along the fertile banks of the Nile, this understanding deepened into something more sophisticated. The Egyptians, whose civilization depended on the annual flooding of their great river, became obsessed with tracking time. They divided the day into segments, created calendars that predicted the Nile's rise and fall, and developed shadow clocks that could indicate not just morning from afternoon, but could divide the day into smaller portions. These early timekeepers were simple constructions, often L-shaped devices with markings along a horizontal bar. As the sun moved across the sky, the shadow cast by the vertical piece would fall across different marks, indicating the passage of hours. In the morning, the device would be oriented one way, and at noon, it would be turned to face the opposite direction for the afternoon hours. What makes these ancient instruments remarkable is not their mechanical complexity, for they had none, but rather the conceptual leap they represented. By creating a device that translated the sun's movement into measurable segments, the Egyptians transformed time from an abstract flow into something concrete, something that could be divided, named, and scheduled around. A priest could know when to perform certain rituals. A farmer could gauge how much daylight remained for work. An administrator could set specific times for meetings or judgments. The shadow clock did not change the sun's journey across the sky, but it changed how humans experienced that journey. It gave structure to the formless, created appointments where before there were only vague intentions to do something later or soon. As centuries passed and civilizations rose along rivers and coastlines, in valleys and on plains, the technology of shadow reading spread and evolved. The Greeks refined the concept into what we now call the sundial, a device of mathematical precision and often considerable beauty. Unlike the simple shadow clocks that preceded them, Greek sundials were calculated instruments, designed with an understanding of geometry and the sun's seasonal paths. The gnomon was angled to match the latitude of the location where the sundial would be used, ensuring greater accuracy throughout the year. The face of the dial was marked with lines that compensated for the sun's changing arc across the seasons. Some sundials were horizontal, others vertical, and still others were hemispherical bowls with the gnomon projecting from the centre, allowing the shadow to sweep across a curved surface marked with hour lines. These sundials became fixtures in public spaces throughout the Greek and later Roman world. In marketplaces and forums, outside temples and government buildings, these devices served as the community's timekeeper. Citizens could glance at the sundial to know whether they were early or late for an appointment, whether the law courts would still be in session, whether there was time to complete business before the day's end. The sundial became so integral to civic life that its absence was noteworthy. We have records of complaints when sundials were not maintained or when their accuracy degraded. Time had become not just observable, but expected, reliable, and increasingly essential to the functioning of complex societies. Yet for all their sophistication and widespread use, sundials possessed an obvious limitation. When clouds obscured the sun, the device fell silent. When night descended, the sundial became useless, its face blank and unhelpful. For thousands of years, human timekeeping was divided between the visible hours of daylight, which could be measured and tracked, and the mysterious hours of darkness, which remained largely unmeasured. The night was a temporal void, a period known only by its beginning and end. This division between day and night, between measured time and unmeasured time, created a fundamental asymmetry in human experience, one that would persist until other technologies emerged to conquer the darkness and bring time's measurement into every hour, every moment, regardless of whether the sun shone or not. The problem of measuring time without the sun's guidance troubled ancient civilizations for centuries. Darkness was not merely an absence of light, but also an absence of certainty. How long until dawn? How much of the night had passed? When should the temple guards change shifts? When should the baker begin preparing bread so it would be fresh for the morning market? These questions had no easy answers when the sky was moonless or overcast, when the sun's reliable shadow vanished for half of every day. The solution would come not from watching the heavens, but from observing something far more earthly and controllable: the steady, patient flow of water. Water clocks, known to the Greeks as klepsydras, meaning water thieves, emerged independently in several ancient cultures, suggesting that the concept was almost inevitable once civilizations reached a certain level of sophistication. The earliest versions were remarkably simple. A container with a small hole near its bottom would be filled with water. As the water dripped out at a relatively constant rate, the level inside the container would drop, and markings on the interior or exterior would indicate how much time had passed. Unlike sundials, water clocks worked equally well in darkness and light, in all weather, at any time of year. They were humanity's first attempt to create time independently, to manufacture temporal measurement rather than merely observe it. The Egyptians were among the first to develop water clocks, with examples dating back to the reign of Amenhotep III in the 14th century before the Common Era. These were not crude vessels, but carefully crafted instruments, often made of alabaster or other fine stone, with interior markings that accounted for the varying lengths of Egyptian seasonal hours. The Egyptians, like many ancient peoples, divided daylight into 12 hours and nighttime into 12 hours, regardless of the season. This meant that a summer daytime hour was considerably longer than a winter daytime hour, and the reverse was true for nighttime hours. Egyptian water clocks had different columns of markings for different months, allowing the priests who used them to read time according to this seasonal system. In ancient China, water clocks evolved into devices of extraordinary complexity. Rather than simple outflow containers, Chinese artisans developed inflow clocks, where water dripped into a vessel rather than out of it. This seemingly minor reversal had significant advantages. Inflow clocks maintained more constant rates because the pressure driving the water remained relatively stable, whereas outflow clocks slowed as the water level and thus the pressure decreased. Chinese inventors also created elaborate systems with multiple tanks, where water would flow from one reservoir to another, with various mechanisms regulating the flow to maintain consistency. Some Chinese water clocks grew into architectural marvels, tower-like structures with complex sequences of tanks and siphons, with the rising water driving mechanical devices, moving figurines, ringing bells, or striking gongs to announce the hours. The Greek and Roman civilizations embraced water clocks enthusiastically, using them not only for timekeeping in temples and public spaces, but also for practical applications in daily life. In Athenian courts, water clocks measured the time allotted to speakers, ensuring that advocates and defendants received equal opportunity to present their cases. The phrase, "his time ran out," may well originate from this practice, as observers could literally watch the water level drop while someone spoke, knowing that when the vessel emptied, the speech must end regardless of whether the argument was complete. Roman engineers refined water clock technology further, creating devices with complex gear mechanisms that could drive hands around a dial face, making the clocks easier to read and more similar in appearance to the mechanical timepieces that would emerge centuries later. What's particularly fascinating about water clocks is how they changed human consciousness about time itself. With sundials, time remained tied to natural phenomena, to the sun's inexorable journey across the sky. The sundial measured something external and independent, but water clocks created time. The steady drip, drip, drip of water was not measuring anything in nature, but rather creating its own rhythm, its own pulse. This was manufactured time, human time, time that we could start, stop, refill, and control. In a sense, water clocks represented humanity's first assertion of temporal independence from the cosmos. We were no longer merely observers of time's passage, but creators and controllers of it. The engineering challenges presented by water clocks drove innovation in unexpected directions. Maintaining a constant flow rate proved surprisingly difficult. Water's viscosity changes with temperature, flowing more slowly when cold and more quickly when warm. Mineral deposits could gradually narrow the outlet hole, changing the rate unpredictably. Evaporation could affect the amount of water available. Ancient engineers developed ingenious solutions to these problems. Some designs used overflow tanks that maintained a constant water level and thus constant pressure. Others employed floats that rose or fell with the water level, moving indicators or pointers to show the time. Some included thermometers and correction charts to account for temperature variations. The pursuit of accurate time measurement drove technological progress in metallurgy, fine drilling, water control systems, and mechanical engineering. Beyond their technical achievements, water clocks also represented something profound about human ambition and priorities. These devices required maintenance, filling, adjustment, and observation. Someone had to tend them to ensure they remained accurate and functional. Societies invested resources and human effort into creating and maintaining these instruments, demonstrating that measuring time had become valuable enough to justify significant expenditure. Time was no longer merely something that happened. It had become a commodity, something worth capturing, preserving, and distributing to the community. The presence of public water clocks in a city indicated a level of social organisation and shared temporal awareness that distinguished more complex civilizations from simpler societies where time remained primarily a personal, subjective experience. Yet water clocks had their own limitations. They required regular refilling, careful maintenance, and protection from freezing temperatures. They were not easily portable. Their accuracy, while impressive for their era, was limited by the fundamental challenges of maintaining truly constant water flow. As human societies grew more complex, as commerce expanded, as navigation became more ambitious, as scientific inquiry deepened, the need for more accurate, more reliable, and more convenient timekeeping devices became increasingly urgent. The water clock had conquered the night and freed timekeeping from its dependence on the sun, but it could not provide the precision that the emerging world would demand. While water flowed through clepsydras and shadows crept across sundials, humanity developed another crucial temporal technology, one that measured time not in hours or minutes, but in days, months, and years. The calendar, that seemingly simple grid of numbered days, represents one of humanity's most important and complex intellectual achievements. Creating a calendar requires understanding multiple celestial cycles that do not align neatly with one another, making compromises between competing systems and establishing conventions that entire societies must accept and follow. The history of calendars is a story of observation, mathematics, politics, religion, and the eternal human struggle to organize our lives within the cosmos's larger rhythms. The moon provided humanity's first calendar. Its cycle is obvious, dramatic, and relatively short, moving from new moon to full moon and back again in roughly 29.5 days. Ancient peoples across the world recognized this pattern and organized their lives around it. Lunar months provided a natural way to divide the year into manageable segments. Many early calendars were purely lunar, with 12 months of alternating 29 and 30 days, totaling 354 days. This created a year shorter than the solar year, the time it takes Earth to complete one orbit around the Sun, which is approximately 365.25 days. The disconnect between lunar months and the solar year created profound challenges. Agricultural societies needed their calendars to align with the seasons, to tell them when to plant and harvest, when frost would come and when it would depart. But a purely lunar calendar drifts through the seasons, with months gradually shifting earlier each solar year. After several years, what began as a summer month would fall in winter. For nomadic or pastoral peoples, this drift might not matter much, but for farming communities, it was unacceptable. The solution was to create lunisolar calendars, systems that followed lunar months, but periodically added extra months to realign with the solar year. The ancient Babylonians developed a sophisticated lunisolar calendar system that influenced much of the ancient world. They observed that 19 solar years contain almost exactly 235 lunar months. This relationship, later known as the Metonic cycle, after the Greek astronomer Meton, who described it precisely, allowed calendars to follow lunar months while remaining synchronized with the seasons. The Babylonian calendar added 7 extra months over each 19-year period, inserting these intercalary months according to specific rules that kept the calendar aligned with both the moon and the sun. In Egypt, a different approach emerged. The Egyptians developed one of the first solar calendars, dividing the year into 12 months of 30 days each, then adding 5 extra days at the year's end to reach 365 days total. This calendar ignored the moon entirely, focusing instead on the sun's annual journey and, crucially, on the Nile's flooding cycle, which was the foundation of Egyptian agriculture and prosperity. The Egyptian calendar was more regular and predictable than lunisolar systems, but it too had a flaw. By using exactly 365 days, it ignored the additional quarter day in the true solar year. Over time, this caused the calendar to drift slowly through the seasons, though the drift was gradual enough that it took centuries to become problematic. The Romans inherited various calendar traditions and struggled for centuries to maintain an adequate system. The early Roman calendar was a lunisolar calendar that required frequent intervention by priests and magistrates to keep it aligned with the seasons. Political manipulation often interfered with this process, with officials adding or removing days to extend or shorten their terms of office or to affect the timing of festivals and elections. By the 1st century before the Common Era, the Roman calendar had become severely misaligned with the actual seasons, causing confusion in agriculture, commerce, and administration. Julius Caesar, guided by the Egyptian astronomer Sosigenes, reformed the Roman calendar in what became one of history's most successful calendar changes. The Julian calendar established a 365-day year with an extra day added every 4th year, creating the leap year system. This gave an average year length of 365 and 1/4 days, very close to the true solar year. The Julian calendar abandoned lunar months entirely, creating months of arbitrary lengths, some with 30 days, some with 31, and February with 28 or 29. These irregular month lengths reflected political considerations, particularly the desire to give months named after Augustus Caesar and Julius Caesar equal prestige by ensuring both had 31 days. The Julian calendar served the Western world remarkably well for over 1,500 years, but it was not perfect. The true solar year is not exactly 365 and 1/4 days, but rather approximately 365.2422 days, about 11 minutes shorter than the Julian calendar assumed. This small discrepancy accumulated slowly, causing the calendar to drift forward relative to the seasons by about 1 day every 128 years. By the 16th century, this drift had accumulated to about 10 days, causing the spring equinox to fall on March 11th rather than March 21st, as it had during the Council of Nicaea in the 4th century. This mattered particularly to the Christian Church, which calculated the date of Easter based on the spring equinox. Pope Gregory XIII commissioned a calendar reform in 1582 that created the Gregorian calendar we use today. This calendar kept the basic structure of the Julian calendar, but refined the leap year rule. Instead of adding a leap day every 4 years without exception, the Gregorian calendar makes century years leap years only if they are divisible by 400. Thus 2000 was a leap year, but 1900, 1800, and 1700 were not. This adjustment gives an average year length extremely close to the true solar year, accurate enough that the Gregorian calendar will not drift by a full day for thousands of years. The transition to the Gregorian calendar was neither immediate nor universal. Catholic countries adopted it quickly, but Protestant nations were suspicious of a reform initiated by the Pope and delayed adoption for decades or even centuries. This created a strange situation where different parts of Europe used different dates for the same day, with Catholic regions 10 days ahead of Protestant regions. Britain and its colonies, including what would become the United States, did not adopt the Gregorian calendar until 1752, by which time the discrepancy had grown to 11 days. Eastern Orthodox countries resisted even longer, with Russia not adopting the Gregorian calendar until after the Bolshevik Revolution in 1918. The calendar's history reveals something essential about timekeeping. Unlike devices that measure hours or minutes, calendars require collective agreement. A single person can use a sundial or water clock independently, but a calendar only functions when society accepts and follows it together. The calendar is social time, coordinating the activities of entire civilizations, scheduling festivals and markets, and planting seasons, creating shared temporal frameworks within which complex societies can operate. Our current calendar, with its arbitrary month lengths, its skipped leap years in most century years, its numbering system marking years from a date 2,000 years in the past, is not natural or inevitable, but rather a human construction, a shared fiction that we maintain because coordinated time is more valuable than perfect astronomical accuracy. As the medieval period dawned across Europe, timekeeping remained dependent on the sun's position, the flow of water, or the burning of calibrated candles and marked incense sticks. These methods served their purposes, but required constant attention and offered limited precision. The Great Change, the revolution that would transform not only how humanity measured time, but how we structured our entire lives, would emerge from an unlikely source. The bell towers of medieval monasteries, where monks sought to organize their days of prayer into precisely measured intervals. Monastic life was governed by a strict schedule of prayers and offices that divided day and night into canonical hours. Monks were called to prayer at specific times, beginning with matins in the middle of the night, followed by lauds at dawn, then prime, terce, sext, none, vespers, and compline through the day and evening. Maintaining this schedule required a reliable way to track time day and night, regardless of weather. Water clocks and candle clocks served this function, but demanded constant attention. Someone had to watch the clock, then ring a bell to summon the community when the appointed hour arrived. This arrangement was both labour-intensive and vulnerable to human error. A drowsy monk might fall asleep during his watch, missing an office entirely. The solution appeared in the 13th century with the invention of the mechanical clock, though exactly when and where this invention first occurred remains historically uncertain. What we know is that by the late 1300s, mechanical clocks were appearing in churches and monasteries across Europe, and their presence was revolutionary. These early mechanical clocks used a falling weight to provide power. A heavy stone or metal weight hung from a rope wound around a drum. As the weight descended due to gravity, it turned the drum, which through a series of gears drove the clock's mechanism. The critical innovation was the escapement, a device that regulated the descent of the weight, allowing it to drop in small, controlled increments rather than falling freely. The verge and foliot escapement, the earliest type used in mechanical clocks, consisted of a vertical axle, the verge, with two protruding pallets that alternately engaged with the teeth of a crown-shaped wheel. Attached to the verge was a horizontal bar called the foliot, weighted at each end. As the crown wheel tried to turn, driven by the descending weight, one pallet would catch a tooth, stopping the wheel. The momentum of the system would cause the foliot to swing, releasing that pallet and bringing the other pallet into position to catch the next tooth. This back and forth action created the tick-tock sound we associate with clocks and, more importantly, divided time into measurable, equal increments. These early mechanical clocks were not particularly accurate by modern standards, often losing or gaining 15 minutes or more per day, but they possessed revolutionary advantages. Once set up and wound, they ran continuously without constant attention. They worked equally well in darkness and light through any weather. They could ring bells automatically at predetermined times, summoning monks to prayer without requiring a human timekeeper. Within a few decades, mechanical clocks spread beyond monasteries to town squares and civic buildings throughout Europe. The appearance of public clocks in town squares marked a fundamental transformation in how communities experienced time. Before public clocks, time was somewhat personal and flexible. People rose with the dawn, ate when hungry, worked while daylight permitted, and slept when darkness fell. Local customs might define certain periods of the day, but these were approximate and varied from person to person. The public clock changed this. Now an entire town could look at the same clock face and agree on what time it was. Markets could open at specified hours. Workers could be expected to arrive at particular times. Curfews could be enforced. Business meetings could be scheduled with precision. The clock synchronized the community, creating what we might call public time, a shared temporal reality that everyone could reference and coordinate their activities around. This synchronization was not entirely welcome. Some resented the clock's tyranny, the way it imposed external structure on previously flexible rhythms. Agricultural work had always followed natural patterns, working longer during harvest and shorter during winter, starting earlier in summer when dawn came early and later in winter when sunrise was delayed. The clock cared nothing for these natural rhythms. An hour was an hour, whether in June or December, whether the sun shone or rain poured. Workers in early industries found themselves governed by the clock rather than by the task at hand or the daylight available. The phrase "time is money" began to take on literal meaning as employers paid by the hour and expected workers to be present and productive for every minute of those hours. Early mechanical clocks displayed only an hour hand. Minutes, those 60 divisions of each hour, were too short an interval for these imprecise mechanisms to measure reliably. The hour was granular enough for medieval life. Knowing that an event would occur in the third hour after noon was sufficient precision for most purposes. But as clockmaking advanced through the 15th and 16th centuries, mechanisms became more accurate and more complex. Spring-driven clocks appeared, replacing falling weights with coiled springs as power sources. This innovation allowed clocks to become smaller and eventually portable. Minute hands appeared on clock faces, requiring greater accuracy and marking a shift toward ever finer divisions of time. The psychological impact of living by the clock cannot be overstated. Medieval people had experienced time as cyclical, seasons and days rolling endlessly in familiar patterns. Clock time was different. It was linear, irreversible, and uniform. Each hour that passed was gone forever, never to return. Time became something you could waste, save, spend, or manage. The clock divided life into measurable units that could be accounted for and optimized. This mechanical quantified view of time aligned with and reinforced the emerging capitalist economy, where efficiency, productivity, and precise coordination became increasingly valuable. The spread of mechanical clocks also drove innovation in metallurgy, gear cutting, and precision manufacturing. Clockmakers were among the most skilled craftsmen of their age, working with tolerances and precision that exceeded almost any other trade. The techniques and tools developed for clockmaking would later influence the development of scientific instruments, machine tools, and eventually the entire Industrial Revolution. The humble clock, initially created to help monks pray on schedule, became a driving force in technological and economic transformation. By the end of the Renaissance, cities across Europe featured prominent tower clocks, their faces visible from streets and squares, their bells audible throughout the town. These clocks were sources of civic pride, often elaborate and beautiful, decorated with astronomical displays, automated figures, and intricate mechanisms. They announced the hours with chiming bells, some playing elaborate musical sequences. They were, in their way, the first public technology, devices that served entire communities, shaping daily life for rich and poor alike. The mechanical clock had taken time out of the sky and out of the flow of water and placed it on a wall, quantified, regulated, and democratized for all to see and follow. The 17th century brought a revolution in timekeeping that would have consequences far beyond the measurement of hours and minutes. In 1656, a Dutch scientist named Christian Huygens invented the pendulum clock, a device whose accuracy transformed both daily timekeeping and scientific investigation. The pendulum clock was not merely an improvement on existing mechanical clocks, but represented a fundamental advancement in precision, reducing daily errors from 15 minutes to just 15 seconds, a 100-fold improvement that opened new possibilities for science, navigation, and the organization of human activity. The principle behind the pendulum clock is elegant in its simplicity. A pendulum, a weight suspended from a fixed point and allowed to swing freely, oscillates at a rate determined primarily by its length rather than the width of its swing or the mass of the weight. This property, called isochronism, was first observed by Galileo Galilei, who, according to legend, noticed that chandeliers in the cathedral at Pisa, regardless of whether they swung in wide or narrow arcs, took the same amount of time to complete each oscillation. This regular, predictable period made the pendulum ideal as a timekeeper. Huygens' genius was in devising a mechanism that used the pendulum swing to regulate a clock's gear train, creating a device far more accurate than any previous timekeeper. The pendulum clock's mechanism was ingenious. The pendulum was connected to an anchor-shaped escapement that rocked back and forth with each swing, alternately releasing and catching teeth on the escape wheel. This design, known as the anchor escapement, provided a more reliable and accurate means of regulating the clock than the verge and foliot escapement used in earlier mechanical clocks. The anchor escapement also allowed for longer pendulums, which swing more slowly and thus can provide greater accuracy. Long case clocks, what we now call grandfather clocks, with their tall wooden cases, were designed to accommodate pendulums up to a metre or more in length, achieving remarkable precision for their era. The impact of accurate timekeeping on scientific investigation was immediate and profound. Astronomers could now measure celestial events with unprecedented precision, determining the exact moments of eclipses, planetary transits, and stellar positions. These measurements allowed for more accurate astronomical tables and deeper understanding of planetary motion. The pendulum clock was essential to confirming and refining Newton's laws of motion and universal gravitation. Physics experiments that required precise time measurement, such as studies of falling bodies or projectile motion, became feasible. The pendulum clock transformed time from a practical tool for organizing daily life into a scientific instrument capable of revealing nature's hidden regularities. Navigation presented perhaps the most critical application for accurate timekeeping. Determining a ship's latitude, its north-south position, was relatively straightforward using celestial observations. Measuring the altitude of the sun at noon or of the North Star at night could reveal latitude with reasonable accuracy using instruments available for centuries. Longitude, the east-west position, was far more challenging. The Earth rotates once every 24 hours, meaning that every hour of time difference corresponds to 15 degrees of longitude. If a ship's navigator knew the exact time at a reference location, such as Greenwich in England, and could determine the local time by observing the sun's position, comparing these two times would reveal the ship's longitude. The problem was maintaining accurate reference time aboard a ship. Pendulum clocks, despite their accuracy on land, were useless at sea. The ship's motion interfered with the pendulum's swing, and temperature changes affected the pendulum's length and thus its period. For centuries, the longitude problem remained unsolved, costing thousands of lives as ships unable to determine their position accurately ran aground on unseen shores or became hopelessly lost in open ocean. The British government offered the Longitude Prize in 1714, promising £20,000, an enormous sum, to anyone who could devise a practical method for determining longitude at sea. The solution came not from astronomy or mathematics, as many expected, but from horology, the craft of clockmaking. John Harrison, an English carpenter and self-taught clockmaker, dedicated his life to creating a timepiece that could maintain accuracy aboard a ship. Harrison's marine chronometers, developed over decades of painstaking work, used balance wheels instead of pendulums, were compensated for temperature changes, and were mounted in gimbals to minimize the effects of the ship's motion. His fourth chronometer, known as H4, completed in 1759, was a pocket watch-sized device that kept time with extraordinary accuracy during sea trials, losing only a few seconds over months at sea. Harrison's achievement was both technical and conceptual. Technically, he solved countless problems related to friction, temperature compensation, and motion resistance. Conceptually, he demonstrated that time could be maintained accurately enough to serve as a navigational tool, that a mechanical device could be reliable enough to trust with human lives. Marine chronometers based on Harrison's designs became standard equipment on ships throughout the 19th century, enabling the great age of global exploration and trade. Accurate navigation transformed naval warfare, commercial shipping, and scientific expeditions. The world became smaller and safer because time could be kept precisely, even in the challenging environment of an ocean voyage. On land, the proliferation of accurate clocks changed how society functioned. Railroad systems, emerging in the 19th century, required precise timekeeping to coordinate schedules and avoid collisions. Initially, different cities kept their own local time, based on the sun's position, creating chaos as railroads tried to publish schedules that made sense across regions where clocks might differ by 30 minutes or more. This led to the development of standard time zones, dividing the world into regions that would all use the same time, synchronized with increasing precision as telegraphs allowed distant clocks to be set according to a master timekeeper. The factory system of industrial production depended entirely on accurate timekeeping. Workers were expected to arrive at specific times, production processes were scheduled with precision, and efficiency could be measured and optimized only when time itself was quantified reliably. The pocket watch became an essential tool for workers in many industries, particularly for railroad employees whose work required split-second coordination. Time discipline, the habit of organizing one's activities according to the clock rather than the sun or personal preference, became a defining characteristic of modern industrial society. By the end of the 19th century, accurate clocks were everywhere, from church towers to railroad stations, from factories to private homes. Time had become standardized, synchronized, and democratized. The wealthy businessman and the factory worker both organized their days according to the same mechanical hours, minutes, and seconds. This shared temporal framework enabled unprecedented coordination and complexity in human society, allowing millions of people to work together in factories, cities, and global trade networks. The pendulum clock and its descendants had transformed time from a natural phenomenon we observed into a human construction we created, maintained and lived within, second by second, hour by hour, day by day. As the 20th century approached, the pendulum clock represented the pinnacle of mechanical timekeeping, but scientists and engineers were already exploring new frontiers. The question was no longer simply how to measure time accurately enough for daily life, or even for navigation, but how to measure time with the precision required for cutting-edge physics and telecommunications. The answer would come from an unexpected direction, from the study of crystals and the peculiar properties of a mineral called quartz. Quartz is silicon dioxide, one of the most common minerals on Earth's surface, found in sand, in granite, in countless rock formations. What makes quartz special for timekeeping is a property called piezoelectricity, discovered in the late 1800s by Pierre and Jacques Curie. When mechanical stress is applied to certain crystalline materials, including quartz, they generate an electrical charge. Conversely, when an electrical charge is applied to these materials, they physically deform slightly. This bidirectional relationship between mechanical stress and electrical charge would prove revolutionary for timekeeping. In the 1920s, scientists realized that if a precisely cut piece of quartz crystal is placed in an electrical circuit, it will vibrate at an extremely stable frequency when voltage is applied. The crystal essentially acts as a mechanical resonator, vibrating at its natural frequency determined by its size, shape, and the way it was cut from the larger crystal. These vibrations occur at frequencies far higher than a pendulum's swing, typically 32,768 times per second for watch crystals, though other frequencies are used for different applications. This high frequency allows for extremely precise time measurement. The first quartz clock was built in 1927 at Bell Telephone Laboratories by Warren Marrison and J.W. Horton. Their device was enormous compared to modern quartz watches, filling an entire room, but it was remarkably accurate, keeping time to within a few thousandths of a second per day. This represented another order of magnitude improvement over even the finest pendulum clocks. For the first time, timekeeping accuracy was limited not by the timekeeper itself, but by the stability of Earth's rotation, which varies slightly due to tidal forces and other factors. Quartz clocks revolutionized scientific research and telecommunications. Radio stations needed to maintain precise frequencies to avoid interference, and quartz oscillators provided the necessary stability. Scientific experiments requiring precise timing, from physics laboratories to astronomical observatories, adopted quartz timekeepers. During World War II, military applications drove miniaturization of quartz technology, leading to portable quartz clocks for navigation and communication systems. The war's demands accelerated development that might otherwise have taken decades. The transition from laboratory instruments to consumer products took several more decades. Early quartz clocks were expensive, complex, and required expertise to maintain. Through the 1950s and 60s, transistor technology and integrated circuits made quartz timekeeping progressively smaller, cheaper, and more reliable. The breakthrough came in 1969 when Seiko introduced the Quartz Astron, the world's first quartz wristwatch available to consumers. It was expensive, costing as much as a medium-sized car, but it demonstrated that quartz technology could be miniaturized sufficiently for wearable timekeeping. The quartz revolution in consumer timekeeping happened with breathtaking speed during the 1970s. As manufacturing techniques improved and electronic components became cheaper, quartz watches plummeted in price, while mechanical watch prices remained relatively stable. Traditional Swiss watchmakers, who had dominated horology for centuries, with their exquisite mechanical craftsmanship, found themselves unable to compete with inexpensive, accurate quartz watches from Japan and other manufacturers. This period, known as the Quartz Crisis, devastated the Swiss watch industry, forcing many historic watchmaking companies into bankruptcy or consolidation. By the 1980s, quartz watches had become ubiquitous. Digital displays, made possible by the same electronic technology that powered quartz oscillators, appeared everywhere. Watches that once represented significant purchases became inexpensive commodities. Children wore digital watches. Quartz clocks appeared in every room of the house, in cars, in appliances. Time had become so cheap and accessible that it was embedded in countless devices, often as a secondary function. A microwave oven displays the time. A coffee maker can be programmed to brew at a specific moment. Timekeeping technology had advanced to the point where it was essentially free, a negligible cost in almost any electronic device. The implications of universally accurate, inexpensive timekeeping were profound. Coordination became easier, and expectations for punctuality more demanding. When accurate timepieces were rare and expensive, being a few minutes late was understandable. When everyone carries a device that measures time to the second, tardiness became a choice rather than an inevitability. Business practices changed as just-in-time manufacturing and logistics became feasible. Knowing precisely when shipments would arrive, when components would be needed, when workers would be available allowed companies to minimize inventory and maximize efficiency. Quartz timekeeping also democratized precision. A child's digital watch kept time as accurately as the finest chronometer. The wealthy businessman and the factory worker both experienced time with the same precision. This leveling of temporal accuracy was historically unprecedented. Throughout most of human history, better timekeeping had been a privilege of the wealthy or a tool of institutions. Sundials required space and stability. Water clocks required maintenance. Mechanical watches were expensive and required regular service by skilled craftsmen. Quartz technology broke this pattern, making precision timekeeping so cheap and reliable that it became universal. Yet, even as quartz watches became ubiquitous, scientists and technologists were pushing timekeeping to even greater extremes. For applications ranging from GPS navigation to computer networks to scientific research, even quartz oscillators were not accurate enough. The variations in quartz crystal vibrations due to temperature changes, aging, and manufacturing variations, though tiny, were significant when precision requirements extended to billionths of a second. The solution would require abandoning mechanical oscillators entirely and instead measuring time using the most regular, predictable phenomenon known to physics, the vibration of atoms. The quest for atomic precision began in the middle decades of the 20th century, pursued by national standards laboratories seeking to define time with unprecedented accuracy. These institutions recognized that as technology advanced, the definition of a second needed to be more precise and more universally reproducible. A second defined by Earth's rotation was problematic because Earth's rotation varies. A second defined by a pendulum swing or a quartz crystal's vibration depended on the specific device being used. What was needed was a definition of time based on an invariable natural phenomenon, something that would be exactly the same in any laboratory anywhere in the universe. That phenomenon would be found in the quantum behavior of atoms. The atomic clock represents perhaps the most remarkable achievement in humanity's quest to measure time. A device so precise that it would not gain or lose a second over millions of years. A timekeeper that measures intervals so brief they were once considered unmeasurable. The journey to atomic timekeeping required understanding matter itself at the most fundamental level, requiring insights from quantum mechanics. the revolutionary theory that describes the behavior of atoms and subatomic particles. Atoms, those basic building blocks of all matter, exist in discrete energy states. An atom cannot have just any amount of energy, but only specific quantized amounts, like a person climbing stairs who must place their foot on one step or another, but cannot hover between steps. When an atom transitions from one energy state to another, it absorbs or emits electromagnetic radiation at a specific frequency corresponding to the energy difference between those states. This frequency is extraordinarily stable, determined by the fundamental properties of the atom itself rather than by any external construction or environmental factor. In 1945, physicist Isidore Rabi proposed using atomic transitions as the basis for a new type of clock. His insight was that if you could create conditions where atoms repeatedly transition between two specific energy states, and if you could count those transitions, you would have a timer of unprecedented accuracy and stability. The frequency of these transitions would be determined by the laws of physics themselves, making atomic time potentially the most fundamental and universal time standard possible. The first atomic clock was built in 1949 by the National Bureau of Standards, now known as the National Institute of Standards and Technology. This device used ammonia molecules rather than atoms, exploiting quantum transitions in the molecule's structure. While revolutionary in concept, it was not immediately more accurate than the best quartz clocks. The breakthrough came in 1955, when British physicist Louis Essen built the first practical cesium atomic clock at the National Physical Laboratory in England. Cesium atoms became the foundation for atomic timekeeping because of their convenient properties. When cesium atoms are in their ground state, their outermost electron can exist in two slightly different energy levels, a quantum property related to electron spin. The transition between these two levels occurs at a frequency of 9,192,631,770 cycles per second. This number is not arbitrary or approximate, but is a fundamental property of cesium atoms, the same for any cesium atom anywhere in the universe. Essen's clock worked by first heating cesium metal to create a beam of cesium atoms, then using magnets to select only atoms in one of the two ground state energy levels. This beam of prepared atoms passed through a cavity filled with microwave radiation, tuned to approximately the cesium transition frequency. When the microwave frequency exactly matched the transition frequency, atoms would flip between energy states. A detector at the end measured how many atoms had changed states, and feedback circuitry adjusted the microwave frequency to maximize this number, effectively locking the microwave generator to the atomic transition frequency. By counting the microwave cycles, the clock measured time. The accuracy of cesium atomic clocks was astonishing. Essen's early device was accurate to within 1 part in 100 million, meaning it would gain or lose less than 1 second every 3 years. Modern cesium fountain clocks, which use laser cooling to slow atoms nearly to absolute zero and let them drift upward through a microwave cavity before falling back down, extending their interaction time with the microwaves, achieve accuracy of 1 part in 10 quadrillion. Such a clock would neither gain nor lose a second for 300 million years, far longer than modern humans have existed as a species. In 1967, the international scientific community redefined the second based on atomic time. Previously, the second had been defined as a fraction of the solar day or the solar year, tying time to Earth's rotation or orbit. The new definition stated that 1 second equals exactly 9,192,631,770 cycles of the radiation corresponding to the transition between two specific energy levels of the cesium-133 atom. This was the first time a unit of measurement had been defined by a quantum property rather than by a physical artifact or astronomical phenomenon. This redefinition had practical consequences. Every major nation established atomic clock facilities that broadcast time signals, allowing anyone with appropriate receiving equipment to synchronize their clocks to atomic standards. The United States operates a cesium atomic clock at the National Institute of Standards and Technology that serves as the primary time standard for the country. Similar facilities exist in England, France, Germany, Japan, and other nations. These clocks are compared with each other continuously, and their collective output defines coordinated, universal time, the international time standard. Atomic clocks enable technologies that require precise time synchronization. The Global Positioning System uses atomic clocks aboard satellites to broadcast time signals. GPS receivers determine their position by measuring the time it takes for signals from multiple satellites to arrive, then calculating the distances to those satellites and triangulating position. Because radio signals travel at the speed of light, approximately 300 million meters per second, even a timing error of 1 microsecond, 1 millionth of a second, would produce a position error of 300 meters. GPS requires nanosecond-level timing accuracy to provide meter-level position accuracy, impossible without atomic clocks. Telecommunications networks use atomic time standards to synchronize digital transmissions. Computer networks rely on time synchronization for security, for coordinating distributed transactions, for logging events in proper sequence. Scientific research from particle physics to astronomy requires precise timing. Stock markets timestamp trades to microsecond precision to establish the sequence of transactions. Modern infrastructure is built on a foundation of atomic time, on the ability to measure and synchronize time to billionths of a second. Yet even atomic clocks are not the ultimate limit of timekeeping precision. Researchers are developing optical atomic clocks that use transitions between energy levels in atoms that correspond to visible light frequencies rather than microwave frequencies. Because visible light frequencies are hundreds of thousands of times higher than microwave frequencies, optical clocks can theoretically be proportionally more accurate. Experimental optical clocks using strontium or ytterbium atoms have achieved precision exceeding even the best cesium clocks, keeping time accurately enough that the time dilation effects predicted by Einstein's relativity become measurable over height differences of mere centimeters. These extraordinary advances in precision may seem excessive, measuring time far more accurately than any practical application requires. Yet history suggests that when measurement capabilities exceed current needs, new applications emerge that exploit that precision. 50 years ago, nanosecond timing seemed unnecessary. Today, it is essential for GPS and countless other technologies. As optical atomic clocks transition from research curiosities to practical standards, they will likely enable applications we cannot yet imagine, technologies that require knowing what time it is with a precision that would have seemed like science fiction only decades ago. The atomic clock represents the culmination of humanity's journey from shadow sticks to quantum transitions, from dividing the day into rough segments to measuring intervals of billionths of a second. Yet this is likely not the end of the story. As our understanding of physics deepens and our technological capabilities expand, even more precise methods of timekeeping may emerge. Time, that most fundamental aspect of existence, continues to reveal new subtleties and mysteries as we learn to measure it with ever greater precision. While scientists pursued ever greater precision in laboratory timekeepers, the devices ordinary people use to tell time underwent their own remarkable evolution. The wristwatch, now so common it seems almost invisible, has a history that reveals changing social customs, technological capabilities, and the gradually evolving relationship between humans and time. This small device worn on the wrist represents a particularly intimate form of timekeeping, time not displayed publicly for all to see, but carried privately, consulted individually, a personal relationship with temporal measurement. For most of human history, portable timekeeping did not exist. Time was something you travelled to discover, walking to the town square to see the sundial or church clock, listening for bells that announced the hours. The first portable timepieces, developed in the 16th century, were spring-driven clocks small enough to carry, though portable is perhaps generous for devices that were often the size of a large orange and weighed several pounds. These early portable clocks were luxury items owned by nobility and wealthy merchants, symbols of status as much as functional tools. By the 17th century, advances in miniaturization allowed true pocket watches, devices small enough to be carried comfortably in a pocket or worn on a chain. These watches were still expensive, still status symbols, but they were becoming more practical. A gentleman could consult his pocket watch to know the time wherever he happened to be, an extraordinary luxury that provided temporal independence. The pocket watch remained the standard for portable timekeeping for nearly 3 centuries, with countless refinements in accuracy, durability, and ease of use, but the fundamental design remained stable. Wristwatches, watches worn on the wrist rather than carried in a pocket, appeared in the late 19th century, but were initially considered feminine accessories, delicate jewellery pieces, rather than serious timekeeping instruments. Men continued to favour pocket watches, viewing wristwatches as impractical and perhaps effeminate. The transformation began during World War I, when soldiers in the trenches discovered that fumbling with a pocket watch while under fire or while holding a weapon was impractical and potentially fatal. Military officers began strapping pocket watches to their wrists with leather bands, and manufacturers started producing watches designed specifically for wrist wear. The wristwatch emerged from the war as a masculine, practical timepiece associated with military service and modern efficiency. By the 1920s, wristwatches for men had become socially acceptable and increasingly common. The design challenges were significant. A watch worn on the wrist experiences more movement and shock than one carried in a pocket. It is exposed to greater temperature variations, to moisture and dust. Early wristwatches were fragile and unreliable compared to pocket watches. Decades of innovation were required to create wristwatches that were truly robust and dependable. The development of anti-magnetic, shock-resistant and waterproof watches occupied watchmakers throughout the 1920s and 30s. Rolex created the Oyster case, sealed to protect the movement from moisture and dust. Various manufacturers developed spring systems that protected the balance wheel from shock. Special alloys resistant to magnetic fields were incorporated into watch movements. By mid-century, wristwatches had evolved into reliable instruments that could function in harsh conditions, from deep-sea diving to mountain climbing to military combat. The wristwatch's cultural significance extended beyond mere timekeeping. It became a highly personal object, often given to mark important occasions, graduations, retirements, anniversaries. Watches were passed down through generations as heirlooms, carrying memories and family history. The choice of watch said something about its wearer, about their taste, their priorities, their self-image. Expensive Swiss watches conveyed status. Rugged tool watches suggested practicality and adventure. Minimalist modern designs indicated aesthetic sophistication. The watch became a form of self-expression, one of the few pieces of jewellery traditionally worn by men in Western cultures. When quartz technology arrived in the 1970s, It threatened this entire cultural ecosystem. Cheap digital watches that kept better time than expensive mechanical watches made the traditional wristwatch's practical function nearly obsolete. Why spend thousands on a mechanical watch that required regular maintenance when a $10 quartz watch was more accurate? The answer, it turned out, was that watches had become about more than accurate timekeeping. They were craftsmanship, tradition, aesthetics, and identity. The mechanical watch industry survived the quartz crisis by repositioning their products as luxury goods and craft objects rather than pure timekeeping instruments. The 21st century brought another challenge to the wristwatch: the smartphone. With mobile phones that display time more accurately than most watches, that are always present in pockets or hands, that offer alarms and timers and world clocks, the practical need for a wristwatch has diminished further. Yet watches persist, evolving once again. Smart watches emerged, combining traditional timekeeping with digital connectivity, fitness tracking, and communication capabilities. These devices represent a return to the watch's original role as a practical tool, but enhanced with capabilities that would have seemed magical to earlier generations. The evolution of personal timekeeping devices reflects broader changes in how humans relate to time. Early portable timepieces gave individuals temporal autonomy, freeing them from dependence on public clocks. Wristwatches made time even more immediate and accessible, always visible with a glance. Digital displays showed exact time to the second, training generations to think of time as precise and quantified. Smartwatches integrate time into a broader network of information and communication, making the watch less about knowing what time it is and more about managing how we spend that time. Throughout these changes, the fundamental human relationship with portable timekeeping has remained consistent. We want to know what time it is without effort, without needing to travel somewhere or ask someone. We want this knowledge to be reliable, accurate, and convenient. Whether the device is a pocket watch on a chain, a mechanical wristwatch with sweeping hands, a digital display showing glowing numbers, or a smartwatch buzzing with notifications, the core desire remains the same: to carry time with us, to have temporal awareness as an extension of our own consciousness rather than as something external we must seek out. The story of timekeeping is not merely about devices that measure hours and minutes, but also about how these devices have fundamentally transformed human consciousness, society, and our understanding of existence itself. Time, once a natural phenomenon we experience through the rhythm of days and seasons, has become something we create, control, and increasingly struggle with. The history of timekeeping devices is therefore also a history of changing human experience, of how measuring time has altered what it means to be human. In pre-industrial societies, before mechanical clocks became common, people experienced time in what historians call task-oriented time. Work was organized around tasks that needed completing rather than specific durations. A farmer would milk cows when they needed milking, harvest grain when it was ripe, mend tools when they broke. Time was circular and seasonal, with the year rolling through familiar patterns. There was time to plant, time to harvest, time to rest in winter. Social events happened when the community was ready, when people had gathered, not at predetermined hours. This relationship with time was flexible, organic, and closely tied to natural rhythms and human needs. The mechanical clock introduced time discipline, a fundamentally different temporal consciousness. Now work was measured not by tasks completed, but by hours expended. Employers paid workers by the hour, expecting consistent effort for every minute. Factory whistles announced starting times, lunch breaks, and quitting times. Tardiness became a moral failing, while punctuality became a virtue. The clock's time was linear, irreversible, and uniform. Every hour was interchangeable with every other hour, every minute equally valuable or equally wasted. This transformation happened gradually over centuries, meeting resistance from people accustomed to older rhythms, but eventually clock time became the dominant temporal framework. The historian E.P. Thompson documented how this transition created conflict and cultural change. Pre-industrial workers often controlled their own pace and schedule, working intensely at some periods and leisurely at others. Industrial capitalism required steady, consistent work, synchronized across many workers. This wasn't merely a change in work practices, but a change in consciousness, in how people experienced and thought about time. The older generation complained that young people were enslaved to the clock. The rising generation saw punctuality and time discipline as signs of moral character and modern sophistication. This temporal transformation had profound psychological effects. The ever-present awareness of time passing, of minutes ticking away, created new forms of anxiety. Time became something you could be behind or ahead of, something you never had enough of. The phrase saving time emerged, treating time as a resource that could be conserved or squandered. Efficiency, doing more in less time, became a cultural obsession. This was different from working diligently or crafting quality products. Efficiency specifically meant optimizing temporal usage, minimizing the time required for any task. The spread of accurate, synchronized time also enabled and required new forms of social coordination. Railroad systems needed schedules that coordinated trains across vast networks, preventing collisions and allowing passengers to plan journeys. This required abandoning local solar time, where every town's clocks showed noon when the sun was highest, in favour of time zones where entire regions used the same standard time. This shift, controversial when first proposed in the late 19th century, represented a profound abstraction. Time was no longer tied to the sun's position, but was instead a social convention, agreed upon and maintained collectively. Telephone networks, electrical power grids, radio and television broadcasting, computer networks, financial markets, and countless other systems of modern life all depend on precise time synchronization. The global economy operates in real time, with transactions occurring simultaneously across continents, coordinated by atomic clocks accurate to billionths of a second. This level of temporal coordination would have been inconceivable to earlier generations. The infrastructure of modern civilization is built on a foundation of precisely measured, universally synchronized time. Yet this temporal precision has created paradoxes. Despite having devices that measure time to nanoseconds, despite having appliances that save labour and vehicles that travel faster than ever before, modern people consistently report feeling rushed, overwhelmed, lacking sufficient time. This time, famine persists even as actual working hours have generally decreased from the 70 or 80-hour weeks common in early industrial times. The explanation may lie not in how much time we have, but in how we experience it. When time is quantified and every moment potentially productive, leisure becomes tinged with guilt. Relaxation must be scheduled, spontaneity planned. The abundance of choices and possibilities creates pressure to optimize every moment, to ensure we're making the best use of our time. The devices we've created to measure time have also shaped how we remember and experience our lives. Before precise timekeeping, memory was more fluid. Events recalled by their relationship to other events rather than by specific dates and times. Now we timestamp everything. Photographs carry metadata showing exactly when they were taken. Social media posts display precise posting times. Security cameras record every second. This temporal precision creates detailed records but may change how memory itself functions. When every moment is recorded and time-stamped, personal memory becomes less about reconstruction and more about retrieval of recorded data. The smartphone era has created an unprecedented relationship with time. These devices don't merely tell time, but constantly demand attention through notifications, reminders, alarms. They fragment attention, creating a temporal experience of constant interruption. Studies suggest that merely having a smartphone nearby, even when not in use, affects cognitive performance and attention span. The device that was supposed to give us greater control over our time instead often controls us, determining when we're interrupted, what claims our attention, how we structure our days. Some contemporary thinkers argue for temporal liberation, for learning to resist clock time's tyranny and recovering more natural rhythms. The slow food movement, meditation practices, digital detox retreats, and similar phenomena represent attempts to escape or at least moderate the relentless pace of modern temporal consciousness. These movements recognize that while accurate timekeeping has enabled remarkable human achievements, it has also created forms of stress and alienation that may be psychologically and socially harmful. The future of human timekeeping remains uncertain. Will we continue toward ever greater precision and synchronization, with atomic clocks evolving into optical clocks and beyond, with time measured and managed at scales beyond human perception? Or will there be a cultural shift, a recognition that beyond a certain point, additional temporal precision serves technology's needs rather than human needs? Perhaps the future involves both directions simultaneously. Increasingly precise time for technological systems that require it, coupled with deliberate cultivation of temporal awareness that prioritizes human well-being over mechanical efficiency. What seems certain is that timekeeping devices, from ancient sundials to modern atomic clocks, have done far more than allow us to measure duration. They have transformed consciousness, enabled new forms of social organization, created both capabilities and anxieties, and fundamentally altered what it means to be human in time. The tick of the clock, the digits on a display, the chime of an alarm are not merely information about time, but are part of time's structure in human experience, shaping how we live, work, remember, and understand our place in the unfolding moments of existence. As we reflect on this long journey from shadow sticks to atomic oscillations, from seasonal observations to nanosecond precision, certain patterns and themes emerge that illuminate not just the history of timekeeping, but fundamental aspects of human nature and civilization. The devices we've created to measure time reveal our deepest priorities, our evolving understanding of nature, and our constantly changing relationship with the cosmos and with each other. Perhaps the most striking pattern is the relentless drive toward precision. Each era's timekeeping was accurate enough for that era's needs, yet each generation sought greater accuracy still. The sundial served ancient civilizations well for millennia, yet water clocks emerged to conquer night's temporal void. Mechanical clocks provided sufficient precision for medieval monastic schedules, yet pendulum clocks appeared to serve emerging scientific and navigational needs. Quartz oscillators exceeded most practical requirements, yet atomic clocks were developed to meet demands that barely existed when the technology was invented. This progression suggests that increasing precision is not merely about meeting existing needs, but creates new possibilities that then generate new requirements. Another consistent theme is the democratization of timekeeping. Ancient sundials in public squares made time accessible to communities, but reading them required literacy of a sort. understanding which hour line corresponded to which time. Mechanical clocks with striking bells democratized time further, announcing hours audibly so even those who couldn't read a clock face would know the approximate time. Pocket watches made time personally accessible, but remained expensive luxuries for centuries. Quartz technology finally made accurate personal timekeeping available to everyone regardless of wealth. Each advance made time more accessible, more democratic, more universally available. This democratization parallels another trend, the internalization of time awareness. Ancient people traveled to observe public timepieces. Later generations carried personal watches. Modern humans wear time on their wrists or check it on phones carried everywhere. Time has moved from distant and external to immediate and personal, from something you seek out to something always present, from occasional awareness to constant consciousness. This internalization has profound effects, creating the temporal anxiety and time discipline discussed earlier, but also enabling the precise personal coordination that modern life demands. The devices themselves tell a story of increasing abstraction. A sundial's operation is immediately comprehensible. Anyone can see that the shadow moves as the sun travels across the sky. Water clocks are slightly more abstract but still intuitively understandable. Mechanical clocks with their gears and escapements require some technical knowledge to comprehend, but the basic principle of regulated motion controlling time measurement remains graspable. Quartz oscillators vibrating at tens of thousands of times per second are difficult to visualize, and atomic clocks measuring cesium transitions at billions of cycles per second operate at scales entirely beyond human sensory experience. As timekeeping has become more accurate, it has also become more abstract, more dependent on scientific understanding rather than direct observation. This abstraction reflects humanity's broader intellectual journey from direct sensory experience toward theoretical understanding. Ancient timekeeping relied on observations anyone could make. Shadows lengthen, water flows, the moon waxes and wanes. Modern timekeeping depends on quantum mechanics, electromagnetic theory, relativity, concepts accessible only through mathematics and instrument-mediated observation. The timeline of timekeeping devices thus mirrors the development of scientific knowledge itself, from empirical observation to theoretical understanding of nature's deepest principles. Consider how different civilizations develop timekeeping independently, arriving at similar solutions despite cultural differences. Sundials appeared in Egypt, Greece, China, and the Americas. Water clocks emerged in Babylon, Egypt, Greece, India, and China. This convergence suggests that certain solutions to timekeeping challenges are natural or inevitable, given particular technological capabilities. Yet each culture also developed unique approaches reflecting specific needs and values. Chinese water clocks emphasized astronomical observation and bureaucratic administration. Islamic cultures developed sophisticated sundials that could indicate prayer times. European mechanical clocks initially served monastic schedules before spreading to civic and commercial applications. Timekeeping technology thus represents both universal human needs and culturally specific priorities. The relationship between timekeeping and power deserves consideration. Throughout history, those who controlled time possessed significant authority. Ancient priests who could predict eclipses and seasonal changes wielded religious and political power. Medieval monasteries that maintained water clocks and rang bells organized entire communities' daily rhythms. European cities competed through elaborate tower clocks that demonstrated civic pride and organizational sophistication. Modern nations maintain national time standards and broadcast time signals, asserting temporal sovereignty. Corporations use precise scheduling and time tracking to control workers' activities. The ability to measure and define time conveys power over those who must coordinate their activities according to that measurement. Yet timekeeping has also been liberating. Personal timepieces freed individuals from dependence on communal timekeepers, allowing private temporal autonomy. Accurate navigation using marine chronometers opened the world to exploration and trade. Standard time zones enabled railroad travel and communication across distances. Atomic clocks provide public time standards available to anyone with receiving equipment, preventing temporal monopolies. The same technology that enables control also permits independence, depending on how it's implemented and who possesses access. The story of timekeeping also reveals the inadequacy of progress narratives that portray history as steady improvement. Different eras require different balances between accuracy, convenience, and cost. A medieval peasant might have been happier with less temporal precision and more flexible daily rhythms than modern workers experience. The Polynesian navigators who traversed the Pacific using celestial observation and understanding of waves and winds possessed temporal and spatial awareness that most modern people have lost, despite our superior instruments. Progress in timekeeping capability doesn't necessarily mean progress in human well-being or wisdom. Looking at the artifacts themselves, from ancient sundials preserved in museums, to mechanical watches ticking in collections, to atomic clocks humming in laboratories, we see human ingenuity, craftsmanship, and creativity. These devices represent countless hours of observation, experimentation, refinement, and innovation. Each advance built on previous knowledge while introducing new principles. The Gnomon's shadow taught lessons applied to water flow, which informed mechanical regulation, which suggested pendulum principles, which led to understanding oscillation, which opened paths to quartz and atomic timekeeping. Knowledge accumulated across millennia, each generation contributing to an edifice that enables our current temporal precision. As we conclude this reflection on timekeeping's history, we might consider what these devices collectively reveal about human nature. We are creatures who observe patterns, who seek to understand and predict, who desire control over our environment, including time itself. We are social beings who require coordination, shared frameworks, agreed upon standards. We are innovative, constantly seeking improvements even when existing solutions function adequately. We are meaning makers who transform mere duration into history, who see in time's passage not merely change, but story, progress, loss, and possibility. The devices we've created to measure time are ultimately mirrors reflecting ourselves, showing our capabilities, limitations, obsessions, and dreams across the ages. Beyond the familiar devices we've explored, the history of timekeeping includes remarkable instruments from cultures around the world, each reflecting unique environmental conditions, technological capabilities, and cultural values. These lesser-known timekeepers remind us that the Western progression from sundial to atomic clock is not the only story of humanity's relationship with temporal measurement. Different peoples in different places developed ingenious solutions to the universal challenge of tracking time's passage. In ancient China, incense clocks provided an elegant solution to timekeeping that engaged the sense of smell rather than sight. These devices burned specially prepared incense along calibrated paths, with the burning rate carefully controlled to provide consistent time measurement. Some incense clocks were simple sticks of incense with marks along their length, but others were elaborate works of art. Incense seals, flat plates with intricate carved channels, would be filled with incense powder. When the powder was ignited at one end, it would burn slowly through the maze-like pattern, taking hours or even days to complete its journey. Different types of incense could be placed in different sections, releasing distinct fragrances to mark different hours without requiring visual attention. A sleeping person might wake to the scent of jasmine and know dawn was approaching. The sophistication of Chinese incense timekeeping reached remarkable heights. Some devices incorporated weights hung on threads positioned over specific points along the incense trail. As the burning incense reached each thread, it would sever the thread, dropping the weight onto a metal plate below with a sound that announced the hour. This created an audible alarm system centuries before mechanical alarm clocks. Dragon-shaped incense burners with incense sticks, as the dragon's body provided both timekeeping and decorative art. The cultural integration of timekeeping into aesthetic and sensory experience represents a different approach from the European emphasis on mechanical precision and public display. In medieval Islamic cultures, astronomers and mathematicians developed highly sophisticated sundials that solved problems European sundial makers would not address for centuries. Islamic religious observance required knowing prayer times, which vary with the sun's position and change throughout the year. Simple sundials showing hours were insufficient. Islamic artisans created sundials that could indicate prayer times specifically, accounting for seasonal variations and geographical location. Some of these instruments combined sundial principles with astronomical calculations, featuring movable components that adjusted for date and latitude, effectively creating analog computers that calculated proper prayer times from the sun's shadow. The Qibla compass sundial represented particular ingenuity, combining timekeeping with directional finding to indicate both the time and the direction toward Mecca. Essential information for Muslim travelers. These portable instruments were precision devices, carefully graduated and adjusted. They required understanding of spherical geometry, astronomy, and geographical coordinates. The mathematical sophistication underlying Islamic timekeeping instruments exceeded contemporary European devices, demonstrating that technological advancement in horology was not limited to any single culture or region. In Japan, Wadoke clocks represented a unique solution to mechanical timekeeping in a culture using temporal hours that changed with the seasons. While European clocks divided day and night each into 12 equal hours, regardless of season, Japanese tradition divided daylight into 6 hours and nighttime into 6 hours, with the length of these hours varying throughout the year. A summer daytime hour might be twice as long as a winter daytime hour. European mechanical clocks with their fixed gear ratios could not accommodate this system. Japanese clockmakers, after being introduced to European mechanical clocks in the 16th century, developed extraordinary modifications to make mechanical clocks compatible with Japanese temporal hours. Some Wadoke had 2 separate foliot balances, one for daytime and one for nighttime, with mechanisms that automatically switched between them. Others used adjustable weights on the foliot that could be moved to change the clock's rate. The most sophisticated featured mechanisms that gradually adjusted the rate throughout the day as the length of the temporal hour changed. These clocks required daily adjustment and represented remarkable mechanical ingenuity, solving a problem European clockmakers never faced because they used equinoctial hours of fixed length. In Tibet and Mongolia, sand clocks took forms unique to those regions. Rather than the hourglass shape familiar in Europe, these cultures developed flat wooden boxes divided into compartments. Fine sand would flow through narrow channels from one compartment to another, with the distribution of sand indicating time elapsed. These devices were portable, required no maintenance beyond occasional sand replacement, and were well suited to nomadic lifestyles. They measured intervals for religious meditation and ritual practices, with different sand colours sometimes used to create visual patterns as time passed. Native American cultures developed timekeeping methods appropriate to their environments and needs. In the southwestern deserts, some peoples created sun markers, carefully positioned stones or architectural features that cast shadows or allowed sunbeams to strike specific points only at particular times of year. The famous sun dagger at Chaco Canyon in New Mexico marks solstices and equinoxes with remarkable precision, created through careful astronomical observation and architectural planning. These were not clocks in the conventional sense, but rather calendrical instruments that mark the year's major turning points, essential for agricultural and ceremonial scheduling. The diversity of these timekeeping traditions demonstrates that there is no single correct approach to measuring time. Each culture developed solutions appropriate to their needs, their available materials, their environmental conditions, and their conceptual frameworks. The Chinese emphasis on sensory time, the Islamic integration of timekeeping with religious observance and astronomical knowledge, the Japanese adaptation of foreign technology to indigenous temporal systems, the Tibetan focus on portability and durability, the Native American attention to annual cycles rather than daily hours, all represent valid and sophisticated approaches to temporal measurement. These varied traditions also remind us that timekeeping is never merely technical, but always cultural. The devices we create embody assumptions about what time is, what aspects of time matter most, how time should be divided, and what purposes timekeeping serves. Western mechanical clocks, with their relentless uniform ticking and their division of day and night into identical hours, reflect particular cultural values: regularity, precision, the separation of time from natural rhythms. Other traditions integrated timekeeping more closely with nature, with religious practice, with sensory experience, or with seasonal change. In the modern era, as global communication and standardized time zones have created increasingly uniform temporal systems worldwide, much of this diversity has diminished. Japanese temporal hours gave way to Western clock hours during the Meiji modernization. Traditional incense clocks became curiosities rather than practical timepieces. Islamic prayer time sundials were replaced by printed tables and eventually smartphone apps. This standardization has brought benefits in coordination and compatibility, allowing global systems of transportation, communication, and commerce to function smoothly. Yet something valuable has been lost: a rich diversity of temporal consciousness and timekeeping practice that reflected humanity's cultural variety. The study of these diverse timekeeping traditions enriches our understanding of the human relationship with time. It reveals that our current system, with its atomic clocks and synchronized digital displays, is not inevitable or natural, but rather one possibility among many. Different choices about how to measure and structure time might lead to different experiences of temporal reality, different relationships between human activity and natural rhythms, different balances between precision and flexibility. By understanding how other cultures approach timekeeping, we gain perspective on our own temporal systems and the assumptions embedded within them. The relationship between timekeeping and navigation represents one of the most consequential connections in human history, transforming exploration, trade, and ultimately the geopolitical structure of the world. The seemingly abstract problem of accurately measuring time became, through the challenge of determining longitude, a matter of survival, wealth, and empire. Understanding how timekeeping enabled navigation illuminates both the practical importance of temporal measurement and the unexpected ways that solving one problem can transform society. Ancient navigation relied primarily on coastal sailing, keeping land in sight and using familiar landmarks. When sailors ventured beyond sight of land, they navigated by celestial observation, noting the sun's position by day and the stars' positions by night. This allowed reasonably accurate determination of latitude, the north-south position. In the northern hemisphere, Measuring the angle of the North Star above the horizon directly gives latitude. Near the equator, measuring the sun's maximum altitude at noon and comparing it to tables of the sun's declination throughout the year yields latitude. These techniques required only relatively simple instruments like the astrolabe or quadrant and some astronomical knowledge. Longitude proved far more difficult. Unlike latitude, which has natural reference points at the equator and poles, longitude is essentially arbitrary. Any meridian could serve as the prime meridian. What matters is the angular distance east or west from some chosen reference point. The Earth rotates once every 24 hours, meaning that every hour of time difference corresponds to 15 degrees of longitude. If a navigator knew the exact time at a reference location, such as Greenwich, and could determine local time by observing the sun's position, comparing these two times would reveal longitude. The challenge was maintaining accurate reference time aboard a ship. Pendulum clocks, despite their accuracy on land, were useless at sea. The ship's motion interfered with the pendulum's swing. Temperature variations affected the pendulum's length. Humidity and salt air corroded mechanisms. For centuries, mariners lacked reliable means to determine longitude, leading to catastrophic losses. Ships ran aground on unexpected shores. Vessels became hopelessly lost, their crews dying of thirst and starvation while sailing past islands they could not locate. Naval battles were lost because fleets could not navigate accurately to rendezvous points. The magnitude of the longitude problem prompted governments to offer substantial prizes for solutions. Spain's King Philip III offered a prize in the early 17th century. The Dutch offered rewards. Most famously, the British Parliament passed the Longitude Act in 1714, offering £20,000, an enormous sum equivalent to millions today, for a method to determine longitude within 30 nautical miles after a voyage to the West Indies. This prize attracted attempts from scientists, inventors and cranks, generating proposals ranging from brilliant to absurd. Many expected the solution to come from astronomy rather than horology. If accurate tables of the moon's position could be created, navigators could determine time by measuring the moon's angular distance from specific stars, comparing this to tables that predicted these distances for every hour. This lunar distance method required no timekeeper, but demanded extensive astronomical tables, complex calculations, and extremely precise angle measurements under difficult conditions aboard a moving ship. While eventually made workable, it was laborious and remained the province of expert navigators. John Harrison's approach was simpler conceptually, but extraordinarily difficult technically. Build a clock that would keep accurate time at sea. Harrison was not a formally trained clockmaker, but a carpenter with genius-level mechanical insight. His first marine chronometer, known as H1, completed after 7 years of work, was a large mechanism weighing 75 pounds. It used linked balances that counteracted the ship's motion, maintaining regular oscillation despite rolling and pitching. Harrison incorporated friction-reducing mechanisms, temperature compensation, and other innovations that kept the clock accurate during sea trials. Despite H1's success, Harrison was not satisfied. He spent decades refining his designs, creating H2 and H3, each incorporating improvements but never meeting his own exacting standards. Finally, he took a radically different approach with H4, completed in 1759. Rather than building a larger, more complex clock, he created a large pocket watch, barely 5 inches in diameter. This timepiece achieved unprecedented accuracy through innovative escapement design, temperature compensation using bimetallic strips, and careful attention to friction and lubrication. During sea trials, H4 kept time accurately enough to determine longitude well within the prize requirements. Yet Harrison faced years of struggle with the Board of Longitude, which was reluctant to award the full prize to a mere craftsman whose solution was not based on advanced astronomy or mathematics. Political machinations, academic snobbery, and bureaucratic inertia delayed full recognition and payment until Harrison was an old man. The story, while frustrating, demonstrated that practical craftsmen could solve problems that eluded theoretical scientists, and that innovation sometimes comes from unexpected directions. Harrison's chronometers were too expensive and complex to mass produce initially, but they proved the principle. Other clockmakers refined and simplified marine chronometer designs throughout the late 18th and early 19th centuries. By the 1800s, marine chronometers were standard equipment on naval and merchant vessels. Ships could navigate confidently across open oceans, opening new trade routes and enabling more precise cartography. The world became more accessible, more connected, and more accurately mapped because time could finally be kept reliably at sea. The impact extended beyond navigation. Accurate marine chronometers enabled scientific expeditions to make precise geographical and astronomical observations. Naval warfare became more sophisticated as fleets could coordinate movements accurately across vast distances. Colonial expansion accelerated as ships could reach distant destinations more reliably. Global trade networks expanded as merchant vessels navigated more safely and efficiently. The humble chronometer, a clock that could withstand a ship's motion, became an instrument that reshaped global power structures. The principle underlying longitude determination, that time and space are intimately connected, would later become central to modern physics. Einstein's theory of special relativity demonstrated that time and space are not separate, but are woven together into space-time, with observers moving relative to each other experiencing time at different rates. The GPS satellites orbiting Earth must account for both special and general relativistic time dilation effects, where time passes slightly faster in orbit than on Earth's surface. These relativistic corrections, amounting to about 38 microseconds per day, would cause GPS positions to drift by kilometers if not corrected. Modern navigation thus depends on understanding time's relationship to space at the most fundamental level. The saga of the marine chronometer illustrates how solving technical problems can have vast historical consequences. Harrison and his contemporaries were trying to build better clocks, but their success enabled exploration, trade, empire, and scientific advancement that shaped the modern world. The connection between accurate timekeeping and geographical position, between knowing what time it is and knowing where you are, created feedback loops between horological development and maritime capability that drove both fields forward. The ticking of a chronometer in a ship's cabin, keeping time while waves rolled and winds blew, was the sound of humanity gaining mastery over Earth's geography, for better and worse. As mechanical and electronic timekeeping reached extraordinary precision, another challenge emerged that required rethinking time itself. How to coordinate clocks across vast distances in an increasingly connected world. The story of time synchronization, of making distant clocks agree on what time it is, reveals the social and technical complexities of shared time. What seems simple in concept, ensuring that everyone's clock shows the same time, becomes remarkably intricate when examined closely, requiring new technologies, international cooperation, and eventual revolution in how time is defined and distributed. Before railroads, different cities kept their own local time based on solar noon, when the sun reached its highest point. This system worked well when travel between cities took days and communication took longer. A few minutes difference between Philadelphia's time and New York's time created no problems when the fastest communication was a letter carried by horseback. But railroads changed everything. Trains travelling at unprecedented speeds required coordinated schedules to prevent collisions and allow passengers to plan connections. A railroad timetable showing departure and arrival times became meaningless when every city along the route used different time. The chaos was considerable. In the United States in the mid-1800s, there were over 300 local time zones, with each significant city keeping its own time. Railroad companies initially addressed this by publishing schedules using the time at major terminals or trying to maintain their own railroad time, but this created confusion for passengers unfamiliar with these conventions. Train stations featured multiple clocks showing different times for different purposes. The situation was unsustainable as railroad networks expanded and interconnected. The solution came through the adoption of standard time zones. In 1883, railroads in the United States and Canada simultaneously switched to a system of 5 standard time zones, each differing by exactly 1 hour from adjacent zones. This was not government mandated, but rather a voluntary coordination by railroad companies recognizing common interest in standardization. The general public initially resisted, some viewing standard time as unnatural interference with solar time. Cities passed ordinances maintaining local time for civic purposes while acknowledging railroad time for travel. Gradually, the practical advantages of standardization won out, and standard time zones were adopted officially. The establishment of standard time zones required choosing a prime meridian, a line of 0 longitude from which all other meridians would be measured. The choice was political as much as practical. Britain, with the world's largest navy and extensive global trade, promoted Greenwich as the prime meridian. France preferred Paris. The United States considered Washington. At the International Meridian Conference in 1884, Greenwich was selected, partly because many existing maritime charts already used Greenwich as their reference. This decision established not just a geographical convention, but also made British time the reference for world time, with other zones defined by their offset from Greenwich Mean Time. Distributing accurate time signals became crucial once standard time was established. Initial methods were surprisingly straightforward. Telegraph lines could transmit time signals from observatories with accurate clocks to distant locations. In the United States, Western Union distributed time signals from the Naval Observatory. Ships in major ports could set their chronometers by observing time balls, large spheres mounted on towers that dropped at precisely noon, visible from across the harbour. This visual signal allowed ships to check chronometer accuracy before departing on voyages where accurate time meant the difference between successful navigation and disaster. Radio transformed time distribution. Beginning in the early 20th century, radio stations broadcast time signals that could be received over vast distances. These signals, originally sent manually but later controlled by highly accurate clocks, allowed anyone with a radio receiver to synchronize their timepieces. Dedicated time signal stations like WWV in the United States transmitted continuous time signals with voice announcements of the exact time. These broadcasts became so reliable that they served as references for scientific research, industrial processes, and eventually for synchronizing early computer systems. The ultimate time synchronization technology emerged with atomic clocks and satellite networks. The GPS system provides time signals accurate to within tens of nanoseconds, available anywhere on Earth with a clear view of the sky. GPS satellites carry atomic clocks and broadcast precisely time-stamped signals. Receivers use these signals both to determine position and to synchronize their own clocks. The Network Time Protocol, developed for computer networks, allows systems worldwide to synchronize to atomic time standards over the internet. Modern infrastructure, from cellular networks to financial trading systems to power grids, depends on this precise time synchronization. Yet synchronizing clocks raises subtle questions about the nature of time itself. In Newtonian physics, time is absolute and universal. There is a single correct time, and clocks in different locations can be synchronized to display that universal time. Einstein's relativity revealed this is not quite true. Time passes at different rates depending on velocity and gravitational potential. A clock in orbit runs slightly faster than an identical clock on Earth's surface. Two clocks at different altitudes experience time at different rates. These differences are tiny for everyday purposes, but become significant for applications requiring extreme precision. GPS must account for these relativistic effects. Satellite clocks, orbiting at high altitude and moving at high velocity, experience time dilation effects that would cause several microseconds of error per day if not corrected. The system continuously adjusts for these effects, effectively implementing relativistic physics in a practical application. This means that GPS doesn't just distribute time, but distributes a corrected, relativistically adjusted time that accounts for the different rates at which time passes in orbit versus on Earth's surface. Modern time synchronization is thus an application of advanced physics, not merely a technical challenge of distributing signals. The social implications of precise time synchronization are profound. Before synchronized time, regional variations in practice and custom were inevitable. Time synchronization enabled, and perhaps required, greater standardization in countless aspects of life. Business hours became standardized across regions. Television and radio broadcasts occurred at specific coordinated times. Factory shifts synchronized across multiple plants. Financial markets opened and closed at precise moments. This coordination enabled efficiencies and capabilities impossible with local time, but it also imposed uniformity, reducing regional autonomy and increasing interdependence. Leap seconds represent a fascinating wrinkle in time synchronization. Earth's rotation is not perfectly constant, but gradually slows due to tidal friction. Atomic time, based on cesium transitions, proceeds uniformly regardless of Earth's rotation. To prevent civil time, which is ultimately based on Earth's rotation, from drifting too far from atomic time, leap seconds are occasionally inserted, typically at the end of June or December. These insertions create brief moments when time is synchronized discontinuously, jumping from 23 hours 59 minutes 59 seconds to 23 hours 59 minutes 60 seconds before advancing to midnight. Computer systems sometimes struggle with leap seconds as they violate assumptions about time's continuous flow. The future of time synchronization may involve abandoning leap seconds entirely, allowing civil time to drift gradually away from solar time. This would simplify technical systems, but would mean that eventually, centuries hence, noon might occur when the sun is not overhead. The debate about leap seconds illustrates deeper questions about whether civil time should track astronomical time or should be purely a matter of convention defined by atomic standards. As timekeeping becomes more precise and more critical to technological infrastructure, these questions gain practical importance beyond their theoretical interest. Time synchronization, from railroad time zones to GPS nanosecond precision, demonstrates that social coordination and technical capability advance together. Each improvement in synchronization enables new forms of coordination, which then create demands for even more precise synchronization. The ticking of millions of synchronized clocks worldwide, all agreeing on what time it is to within billionths of a second, represents an extraordinary human achievement. Yet it also represents a form of temporal homogenization, a world where local time and local rhythms are subordinated to global standards maintained by atomic clocks and satellite networks, where time is no longer discovered by observing the sun, but is distributed as a technological service, precise, universal, and somewhat divorced from the natural world that once defined time's passage. Having traced timekeeping from ancient shadows to atomic precision, from local solar observations to globally synchronized nanoseconds, we might pause to consider what has been gained and what has been lost in this long progression. The story of timekeeping devices is not simply one of continuous improvement, of primitive giving way to advanced, but rather a more complex narrative involving trade-offs, transformations in human experience, and profound changes in how we understand ourselves and our place in the cosmos. The gains are obvious and extraordinary. Modern civilization depends absolutely on precise timekeeping. GPS navigation, requiring nanosecond timing accuracy, enables everything from driving directions to aircraft landings to precision agriculture. Telecommunications networks use synchronized time to coordinate billions of digital transmissions. Financial markets timestamp trades to microsecond precision, essential for determining transaction order and preventing manipulation. Electrical power grids synchronize generators across continents. Scientific research from particle physics to astronomy to neuroscience requires precise timing. Modern life as we know it would be impossible without the accurate, synchronized timekeeping that atomic clocks and distribution networks provide. Beyond practical applications, precise timekeeping has enabled profound scientific discoveries. Accurate clocks allowed confirmation of special and general relativity's predictions about time dilation. Atomic clocks sensitive enough to detect gravitational effects have measured how time passes at different rates just centimeters apart vertically, confirming Einstein's predictions with extraordinary precision. Millisecond pulsars, rapidly rotating neutron stars, serve as natural clocks that allow tests of gravitational wave theories decades before direct detection. The GPS satellites themselves constitute a relativistic experiment, demonstrating daily that relativistic corrections are necessary for accurate navigation. Precise timekeeping has become a tool for understanding the universe's fundamental nature. Medical technology benefits from precise timing. MRI machines coordinate radio pulses with magnetic field changes in precisely timed sequences. Pacemakers deliver electrical pulses at controlled intervals. Radiation therapy depends on precise delivery timing. Research into neurological timing reveals that the brain processes events at millisecond scales, with timing differences of a few milliseconds affecting perception and cognition. Understanding and treating neurological conditions increasingly involves understanding timing at scales that would have been impossible to measure without modern instrumentation. Yet these gains came with costs, some obvious and others subtle. The most apparent is the temporal anxiety discussed earlier, the sense of time pressure and scarcity that pervades modern life. When time is precisely measured and every moment potentially productive, leisure becomes difficult. The tyranny of the schedule, of appointments and deadlines, creates stress that pre-industrial peoples rarely experienced. Some argue this stress contributes to modern epidemics of anxiety and depression, though isolating timekeeping's role from countless other factors in modern life is challenging. More subtly, precise timekeeping has contributed to disconnection from natural rhythms. Humans evolved to wake with sunrise and sleep after sunset, with activity levels modulated by seasonal daylight variation. Artificial lighting allowed violation of these rhythms, but clocks and schedules enforced it. The night shift worker, the long-distance traveller crossing time zones, the teenager staying awake past midnight on social media, all experience circadian disruption impossible in pre-electric eras. Research increasingly links circadian disruption to health problems, including obesity, diabetes, cardiovascular disease, and cancer. Our biological clocks, tuned by millions of years of evolution to Earth's day-night cycle, often conflict with the mechanical and atomic clocks that govern modern schedules. The seasonal disconnect is equally profound. Agricultural societies necessarily lived by the seasons, planting in spring, harvesting in fall, observing natural cycles. Modern urban dwellers can live almost oblivious to seasons, experiencing them as minor variations in weather rather than fundamental rhythms governing life. Climate-controlled buildings, year-round food availability, and work schedules independent of daylight all reduce seasonal awareness. This disconnect may contribute to the environmental crisis as people lose direct experiential connection to natural systems and their cycles. Precise timekeeping has also contributed to the acceleration of life's pace. When manufacturing processes can be timed to the second and optimized continuously, when financial trades execute in microseconds, when communication is instantaneous, the expected pace of everything accelerates. Waiting that previous generations accepted as inevitable becomes intolerable. Patience becomes difficult to cultivate. The expectation of immediate response, whether to emails or text messages or customer service inquiries, creates pressure that compounds over time. Life in industrial society was already fast-paced, but life in the digital age, with its nanosecond synchronized networks, approaches a pace that may exceed human cognitive and emotional adaptation capabilities. There are deeper philosophical losses as well. Ancient peoples experienced time as cyclical, as patterns repeating endlessly. Seasons returned. The moon waxed and waned. Life and death and life again in eternal cycles. This cyclical time consciousness fostered certain attitudes: acceptance of natural processes, comfort with recurrence, reduced anxiety about individual mortality as part of larger cycles. Clock time is irreversibly linear. Each second passes never to return, each moment unique and unrepeatable. This linear temporal consciousness may contribute to heightened mortality anxiety, to the sense that time is running out, to obsession with productivity and leaving a legacy. The metaphysical question of what time actually is becomes more puzzling as we measure it more precisely. Is time a fundamental feature of reality or an artifact of consciousness? Does time truly flow, or is that flow an illusion created by conscious experience? These ancient questions persist despite our ability to measure time to 18 decimal places. Precise measurement has not brought us closer to understanding time's essential nature. Perhaps it has even distanced us, replacing experiential understanding with technical mastery, knowing how to measure time without knowing what time is. Some contemporary movements attempt to recover healthier relationships with time. The slow food movement emphasizes taking time to prepare and savor meals, rather than optimizing eating for speed. Meditation practices train attention to the present moment, rather than constant planning for future or rumination about past. Digital detox retreats encourage temporary disconnection from the devices that fragment attention and impose constant time pressure. Forest bathing and nature immersion practices help people reconnect with natural rhythms. These movements recognize that while precise timekeeping enables modern life's benefits, it has also created pathologies that require conscious resistance and alternative practices. The challenge going forward is maintaining timekeeping's benefits while mitigating its costs. We need GPS and telecommunications and synchronized power grids, but we also need sleep and seasonal awareness and freedom from constant time pressure. We need schedules and coordination, but we also need flexibility and spontaneity and alignment with natural rhythms. Perhaps future societies will develop sophisticated technological infrastructure that maintains precise timing for systems that require it while allowing humans greater temporal freedom in daily life. Automated systems could handle the nanosecond coordination while humans operate on more natural timescales. Alternatively, we might recognize that some degree of temporal alienation is the price of modern civilization's capabilities, accepting this cost as worthwhile for the benefits gained. Every technology involves trade-offs. Precise timekeeping gives us capabilities our ancestors could barely imagine, enables coordination at scales previously impossible, and allows scientific understanding that reveals nature's deepest secrets. If this comes at the cost of some anxiety and disconnection from natural time, perhaps that is a bargain worth making, provided we recognize the costs and work to mitigate them where possible. What seems clear is that the devices we've created to measure time have transformed us as thoroughly as we've transformed them. From beings who lived within time's natural flow, we've become beings who create, control, and optimize time. We've gained extraordinary capabilities and lost something harder to define, but nonetheless real. Understanding this history, recognizing what we've gained and what we've lost, may help us make wiser choices about our relationship with time going forward, using our temporal mastery for human flourishing rather than allowing our clocks to master us. As our journey through the history of timekeeping draws to a close, we find ourselves at a remarkable moment in humanity's relationship with time. We possess technology capable of measuring temporal intervals with precision that would seem almost magical to earlier generations. Yet paradoxically, we struggle with time management more than perhaps any previous era. We carry devices synchronized to atomic standards, accurate to billionths of a second, yet we complain constantly of having no time. This tension suggests that our relationship with timekeeping continues to evolve in unexpected ways. The immediate future of timekeeping technology points toward even greater precision. Optical atomic clocks, currently in research laboratories, achieve accuracy so extraordinary that they would not drift by a second over the entire age of the universe. These devices measure atomic transitions corresponding to visible light frequencies rather than microwaves, vibrating hundreds of thousands of times faster and thus allowing proportionally greater precision. Some experimental clocks can detect gravitational time dilation over height differences of mere centimeters, opening possibilities we are only beginning to explore. Space exploration introduces fresh temporal challenges. On Mars, where days last 24 hours and 39 minutes, future settlers must decide whether to maintain Earth time or adopt Martian schedules. Lunar bases, where the sun rises only once every 28 Earth days, will require entirely different temporal frameworks. As humanity becomes multiplanetary, our timekeeping will necessarily diversify, with different worlds keeping different local times while synchronizing for communication. Time's relativity becomes a practical concern rather than merely theoretical curiosity. Yet even as technology advances, cultural resistance to temporal tyranny grows stronger. Movements advocating digital well-being, the right to disconnect, and slow living recognize that constant time pressure harms human flourishing. Some nations now protect workers legally from after-hours communication requirements. Smartphone features help users manage notifications and limit usage. There is growing awareness that while precise timekeeping enables modern civilization's benefits, it has also created pathologies requiring conscious resistance. The philosophical questions about time's nature remain as mysterious as ever. Is time fundamental to reality, or does it emerge from deeper processes? Does the present moment have objective existence, or is it merely a feature of consciousness? Some physics theories suggest time itself might emerge from timeless quantum processes at the universe's deepest levels. If true, even our most precise atomic clocks would be measuring something ultimately emergent or perhaps illusory. Precision has not brought us closer to understanding what time actually is. Looking back across this long history, from shadows on ancient sundials to quantum transitions in optical lattices, we see that each generation developed timekeeping appropriate to its needs. Each advance transformed not merely how we measure time, but how we experience existence itself. The devices we have examined represent human creativity and the patient accumulation of knowledge across millennia. They show our species solving problems through observation, experimentation, and refinement of ideas passed through countless generations. Yet this history also teaches humility. Each advance brought unintended consequences alongside benefits. Mechanical clocks enabled industrial coordination but destroyed flexible work rhythms. Quartz technology democratized precision but threatened traditional craftsmanship. Atomic standards make GPS possible, but perhaps deepen our disconnection from natural cycles. Progress has never been purely beneficial. Recognizing these complexities allows more thoughtful choices about future developments. The future will be shaped not by technological capability alone, but by human values and choices. We can decide what to preserve from older ways of experiencing time and where to resist letting clocks dominate life. Perhaps future generations will regard our temporal anxieties with bewilderment, wondering why we allowed schedules to tyrannize us. Or they may see our era as transitional, a period when humanity learned to balance technological precision with human needs for flexibility and natural rhythm. As you prepare for sleep, as darkness surrounds you and the day concludes, you participate in an experience humans have shared across all history. The sun has set, night has fallen, and time continues its steady progression. Unlike distant ancestors, you know precisely what time it is, synchronized to atomic standards. Yet the fundamental experience remains unchanged. Your body grows tired. The day's concerns fade. Sleep approaches with ancient, irresistible pull. In this moment, you connect with every human who has ever lived. All of us travelers through time, moving forward moment by moment, measuring the journey as best we can with whatever tools our era provides. The clocks continue through the night. Digital displays glow softly. Atomic transitions occur in laboratories, billions of oscillations per second maintaining time's standard. Satellites orbit overhead, chronometers coordinating signals. The vast infrastructure of timekeeping operates ceaselessly, maintaining the temporal framework civilization requires. But for you now, measured time can fade. Sleep approaches, bringing release from time's demands, from schedules and deadlines, from constant awareness of passing minutes. This nightly release connects you to something ancient. Sleep remains unchanged across millennia, a biological necessity, a reminder that beneath all our technologies, we remain creatures of nature. The most sophisticated atomic clock cannot eliminate the need for rest, cannot free us from fundamental rhythms governing living things. As drowsiness deepens, the elaborate history of timekeeping fades in importance. What matters now is the simple, timeless experience of yielding to sleep, letting go of the day, trusting that morning will come. Sleep well, knowing you are part of time's great river, flowing always forward, carrying all humanity through days and nights, seasons and years. We measure it as best we can, live it as fully as possible, and surrender to rest when each day ends. The clocks keep their vigil. Time flows on. and you rest as humans have always rested since long before anyone thought to measure time, and as humans will rest long after our current devices become historical curiosities. Rest now. Time continues. Sleep comes. All is well.